So, hello, good morning to everybody. First of all, I'd like to thank the Clarice and Marcel. Thanks for the organizers to invite me here. It is a really great pleasure to talk in this audience about my work, which is, very related with quantum mechanics, but in a speculative way related with quantum biology. But since I'm here, I'm trying to provoke a little bit the discussion about what's the relation with quantum biology in this case. So what I'm going to talk about is how to actually harness this spontaneous emission to build quantum networks. That's technically what I do, but I want to pose a more general question also for the audience. And what I learned throughout time is that to explain my work, actually, I need to call attention about a concept that's called global quantum system, because usually for physicists, when we learn quantum mechanics, we start studying isolated quantum systems, and then we describe these quantum systems using a wave function. But then when we learn a little bit more and you start to compare with experiments, you learn that's necessary to describe the system as an open quantum system, okay? A system that is connection with the rest of the world. And then you start to move away from the wave function and you start to move to a different object, what's called a density matrix, which embodies everything that you don't know about the system. So the system starts to behave more in a statistical manner. But as I was involved in my work, I learned, and I had to learn, that actually it's even more realistic to go back to quantum and just quantize the rest of the world, okay? And then when you do that, then you need to go back to the wave function. But what's the tricky thing here is that this is an intrinsically multipartite system. And this is actually the subject of a more recent field related to quantum mechanics, which is now called quantum information. So in this intermediate realistic manner, actually, we are addressing individual systems in contact with one another. But in this more global quantum system way, you need to address all interactive systems to actually realize the quantum properties of the system. And maybe in a provocative way, I could say that the biologists might be a little bit careful when talking about to physicists, because physicists likes to be here. And biology probably is more here. And this is also new physics. So there is a problem of methodology, not only on the biological side, but also on the physics side. And so there is this very famous discussion about the coherence. This is a famous picture in an article by Zurich, in which he describes that there is a quantum world that's kind of fuzzy, and then there is a classical world, and the effect that connects these two worlds is decoherence. And I would argue that actually this is a more or less a 1980s, 1990s view, because in the 1980s, actually we solved the remaining doubts about the validity of quantum mechanics. And after that, what we have is basically that there is no classical world, okay? There is just quantum mechanics. And this actually means that the coherence, I don't think there is a fundamental value for the coherence. This just means that the system is not isolated. And the difference in quantum information is that now we love non-isolated system, because this means that you have quantum entanglement. And what's more interesting that nowadays, I think we need to think about decoherence as an opportunity, okay? Because decoherence means transduction. It means that you have some information in one form of energy or in a material system, and it's also transforming into another kind of system. And that's what we're being noticing in these last years. It is the appearance of many new different fields that explores this transduction. For example, now we have a huge field that's called optomechanics that explores the transduction between light and mechanical modes, and quantize the mechanical modes. And then you have, instead of just seeing how you can lose information from the mechanical modes, let's quantize the mechanical modes and let's use it. And you have also, for example, to do a Magnonic systems, you have many different flavors of magnonic systems. You have cavity optomagnonics, you have cavity electromagnonics, cavity nanomagnonics, quantum magnonics. So you have electro-optomagnonic systems. So there are all sorts of different systems that are being quantized in a more radical way and being used to develop new quantum technologies. The oldest one of this process that we actually learn how to model from first principles, the decoherence, and then we were able to use this for applications, is actually spontaneous emission. And this is the focus of my talk. So that's the oldest of these problems. So what's the spontaneous emission? So first of all, this is a ubiquitous phenomenon. Spontaneous emission is just the light that we see. So if you see light shines in a body and then it moves away in a different direction and gets to your eyes, that's why the body that you are seeing spontaneously emitted a photon to your eyes. And so, but actually the name came from the beginning of quantum mechanics when Bohr did a model for this atom. And then he had to answer the question of why the atom would go from an excited state to the ground state. It just would go through a jump. And he said, okay, so let's call this spontaneous emission because I don't know the cause. So spontaneous means without a cause in this sense. But in 1917, he's still calling spontaneous emission. Already knows that if you quantize the energy of the photon, you should also quantize the momentum. So there are other implications for this spontaneous emission. But only in 1927 by Dirac, with the development of a theory called quantum electrodynamics, that was the first theory that actually explained from first principles spontaneous emission. That's when you start to really quantize completely the problem. And in that time, so he explained the problem by interaction with vacuum modes, and then he could predict the rate of decay of the atoms. So this theory nowadays that what's the most popular theory for spontaneous emissions due to Vasco-Vigny in the 1930s. So what this theory says, this theory is just consider that you have a single atom in the excited state, and then it's interacting with a vacuum of of a large bath of waves, of plane waves of light in this lowest energy level. And when it does that, through the coherent interaction with the vacuum modes, then the atom gets to the ground state. So this was conceptually important throughout decades, because that was a first principle mathematical derivation of an irreversible process. And you could model a decoherent process from first principles. So, but what's usually put aside throughout the decades is that this is not the whole story, okay? Because when this atom goes to the ground state, it's not actually exactly in this state, okay? This is actually a very complex state because you don't know in which direction the atom emits the photon. And depending on the direction, the atoms suffer a recoil. And then actually, the state is a superposition of all recoil states and directions of emission. And this is actually a highly entangled state between atom and light. That's the simplest that you can get from nature in a spontaneous emission. And actually, this just highlights the problem in quantum mechanics, which is a problem that you have a lot of complexity at the bottom of your physical description. So, but let's hard experiment to do, at least for me to do. Well, I can work better with ensembles of atoms. So I'm going to move for a simple system, which is just a collection of pure two-level atoms in a cloud. And I'm going to excite the system with a laser, and I will observe the scattering of light in different directions due to spontaneous emission. And what's the interesting in this system is that it's one of the simplest quantum systems that you can model the light-matter interaction. And you have widely applied classical and semi-classical models to explain this kind of phenomenon. However, there are a couple of challenges. First, there's a lack of structure in this scattered light, which means it's hard to filter like quantum components from from less quantum components, let's say. But what we have is something like this. So the experiment that I was showing you is just this laser passing through a cloud of atoms in vacuum. So this is, I have a vacuum chamber and I can trap some atoms at around 100 microkelvin temperature. And then I shine light on them. I prepare them in a state where the light only connects two states inside the atoms. So that's how I have a pure two-level system. And I detect light not in all directions. I choose one particular direction, we form in a certain angle, and I detect the light here, and I divide the light between two detectors. And what I get from this kind of measurement is a correlation between light, between the intensity of light in a certain time t and the intensity of light at t plus a delay tau. And then I normalize this quantity. Well, so what I observed from the experiments is that this correlation goes from 2 at 0 to 1 for a large delay. What this means? This means in quantum optics that I have a classical system. This is a thermal light source, behaves exactly like this. You have this correlation at 0 delay, and then you to infinity, you go to no correlation, which just means this correlation function goes to 1. So it could look like this is a classical or semi-classical system. But actually, if you look with a quantum information perspective, you will see this. If atoms absorb momentum in this direction and emitted in this direction, so there is some momentum that is left in the atomic system. There is no conservation of momentum here. So there is some information that is left in the atomic system. And actually, if I could see that information, then I could perhaps see the quantum nature of the process. And so what we can do this. We can actually shine light in the other direction. And for this particular system, I'm able to reverse in time and extract the atomic information in a different direction with also a light field. So this configuration is called like a four-wave mixing because you conserve momentum and energy, and then you can have an emission of light in one direction, and then you can have the conjugated emission in the other direction. And then we can detect, we can make correlations between these detectors, or among the two detectors. And you end up with a quantity like this, okay? You have this quantity R, which is a cross correlation squared. This cross correlation is basically the same correlation between intensity in one time with intensity in a later time, but between detectors in the two directions. And these are autocorrelations, which means that that's the detections for this pair of detectors and that pair of detectors independently. And this is a result from quantum optics. So every time that you say that you have something that's purely quantum, is actually you are saying that you have a particular idea of what is classical, okay? So this classical means that it behaves as if light was a well-described function and not a strange wave function. This comes from fault detection theory. And if you have this quantity is smaller than 1, then this indicates classical correlations. Notice from my previous slide that the two fields are thermal fields. So they look like semi-classical or classical states of light that are equal to. But if I have a cross correlation larger than 2, then I enter in this quantum regime. And that's what we measure. So we measure something above 2. Okay, so indicate that we have the quantum nature of this process. So this gray region is that measurement of that quantity R, and then we are above here for some of delays. And for those in the audience that are used to measure quantum correlations, this is a tiny quantum correlation, but is a correlation that measure without filtering. So you actually have the whole Haley scattering background, and the quantum correlation in this system prevails over the classical background. Okay? And so the bottom line here is that the classical models may predict some experimental results, but not all. And this is crucial to understand because I like this work to highlight that if you use semi-classical models or classical models, you end up only making semi-classical questions or classical questions. You need to make completely quantum models if you want to make quantum questions, basically. And then you probe different quantities. And I will call another thing, some attention here for detail, which is this correlation is really fast. And this indicates a process that we call superradiance. That is another universal process. The superradiance was a process that was discussed in the 1950s by Dick. And he called the attention that you can have, I mean, we are in a system where we have a high density of atoms. And then the atoms, when they get excited and then they go down to the ground state, they can go, you can think that they go independently, but actually it's the same vacuum that all the atoms are interacting with. So you end up having interactions between the atoms through the shared vacuum modes. And this actually leads to coupling of the atoms through the vacuum. And this process that goes from a group of atoms from the excited to the ground state, actually, if you have a low density of atoms, you can model as independent process, each atom moving, emitting independently. But when you have a high density of atoms, then you have more directionality of the emission, and you have faster emissions. And this is actually an ubiquitous phenomenon. You see, this is recurrently in many different systems. But I'll move now to the second simplest process with Raman scattering. In Raman scatters, that's the simplest process in which light spontaneously emits a photon, but the photon has a frequency that's different from the one that's absorbed. So here I consider a 3-level atom, and I pump all atoms initially to one of the ground states. And when I excite one of the transitions, then I have some small probability of emitting a spontaneous photon in this other transition. And this end up really generate a complex entangled state where you can have 0 photons in field 1 and 0 atoms transferred to S, or 1 photon in field 1 and one atom transferred to S. And when I say 1 atom, it's not just 1 atom. It just means that I have 1 atom transfer, but I don't know which one. And this is actually called a symmetric Dick state. And that's what is responsible for the superradiant behavior of the last slide. Actually, these entangled states occur very naturally in matter in all situations once you try to describe it from first principles. That's really a ubiquitous effect. But then what we do different is that we detect the light. And then when we detect the light, actually in the system, we can project what's left in the atomic ensemble in a single excitation state, which is a very high quantum state. And notice the detail here is that this click, that's what I call a measurement in the quantum reservoir. So if I don't look to the field in the reservoir, which is here, the vacuum modes, then I can't see the formation of this state. But once I look, I can see the formation of a single photon state. So this is different from the 2-level system that I just described. The quantum correlations here are much stronger. So if I measure that quantity that I call cross correlation, and I measure before 2.6, 3, for this kind of system, this is like 600. Okay, so it's highly quantum system. And you can also revert in time, and then you can come with a read field and transform this collective excitation in another photon, and then you can see the superradiant emission in this point. And then this is an experiment that we did there in Recife as well, where we show the single photon nature of this process, of this superradiant process. And basically, we show that we have a suppression of the 2 photon components. So we have just a single photon, but we have an accelerated decay due to collective enhancement. And in the end, you have this, a single photon emitted collectively. This is really typical of quantum phenomena. This is just a multiple slit experiment with 1 particle, because you don't know through which atom the atom passed through. So it's like a multiple slit, but you have just 1 atom that was excited. So that's the kind of phenomena that also reveals its quantum nature. But so if you think about the vacuum system, I'm just hitting the audience for Ado talk in a moment. So you can get all these non-classical correlations. You don't need the atoms in a vacuum. You can do this in water at room temperature. So he's going to talk about this. And so he's going to talk about this Cauchy-Schwarz inequalities and the Raman scattering. And this is really ubiquitous phenomenon. But the crucial thing is that if you want to see the quantum correlations, you need to know where to look at. If you don't know, it looks like noise. Okay. And so what we can do with that? Actually, we can build things that we call quantum networks. Imagine a very simple process. You have this ensemble of atoms, and then you emit a photon, you don't know when, but you do this simultaneously in two ensembles of atoms. And then you merge these photons in a beam splitter, and then you detect a click in a detector. And this actually results in an entangled state in which you have one atom exciting one ensemble and zero in the other, or vice versa. That's a very, quite almost trivial way to generate entanglement, but it does, okay? Of course, the hard part is not to detect the photon. The hard part is to show that there is actually an entanglement here. So we had to do a tomography of the state that's left in the ensemble. So these ensembles were actually separated by around 3 meters. And we measure the concurrence of the state. So this is already an analysis that comes from quantum information. So every time we discuss these correlations between systems with different parts, you end up in quantum information and the methodology to really clarify what you're seeing. So this is one example of a quantification of entanglement in the system. However, if you have two of these systems in parallel, then what we could do is that we can actually, since now we have two excitations, you can actually just violate a Bell inequality, a Bell inequality in polarization. And what this means that you can do quantum cryptography, okay? So that's another nice thing about quantum information is that it gives a measure of function. It says that, okay, you don't only have entanglement. You have entanglement in a way that you can do something with this entanglement. And actually, this is the genesis of a large field that's quantum networks that were originally proposed in 1997 with atoms in a cavity. It's a theoretical model, but was later expanded to this notion of quantum internet. And now it also comprises not only atoms in a cavity, but also these ensembles in free space. Nowadays, this quantum internet looks more reality since this result by a Chinese group in 2017, in which they could distribute using the photons from para-American down conversion that Gabriela just told you about. They could distribute quantum entanglement in the Earth's surface for distance that were larger than 1,000 kilometers. And so there is a real perspective of a network of these satellites up to 2030, really using quantum entanglement to do cryptography or to just do teleportation and things like this. And so what's the bottom line here? What I will discuss up to now is quantum information, which you can understand as an engineering of artificial phenomena to explore quantum entanglement. But, is there a larger role in natural phenomena to quantum entanglement between light and spontaneous emission? And if there is a larger role, then we can have some hints also from quantum information. The first hint is, oops, I cannot go back. Can I? Oh, I can. So first of all, there is much more information that can be stored in correlation in distinct systems than on isolated systems themselves. So for example, a measurement of two distinct systems may result in truly random results in each of them, but the random results occur concurrent in the two systems, okay? In another way to say this is that it's possible to have zero information on an individual system and a lot of information on the correlations. Also, the amount of information that can be stored in the correlations grows really fast as the number of interacting systems increases, much faster than can be stored separately on the individual systems, which basically means that it's more complexity. So as a conclusion and some bio perspective, so nowadays, we understand our understanding of spontaneous emission evolved to evolve, and now we are able to use it to create complex entangled states and for many applications. I just mentioned a few. I mean, there is a huge number of applications of the spontaneous emissions from atomic systems. And if now we see quantum entanglement as a physical resource, nature likely applies it extensively to multiple tasks. So biological systems should benefit considerably from quantum entanglement because you have a system with strong interaction, with exchange of energy momentum in multiple forms. You need to perform complex synchronized tasks. You need to transmit and manipulate information. And you need to you have confined systems like cells with a lot of internal activities and tasks. So we learn how that to process information is better to process using quantum mechanics. To communicate, quantum mechanics has many advantages. So it's for people that work in quantum information, it's quite strange that nature doesn't use that. But it's much more reasonable that we don't recognize that, because most of this process, if you don't know where you're looking, it just looks like noise or decoherence. So I would like to call attention to this point that, I mean, there is a lot of things that we need to learn and look in this quantum system. And I think biology is one of the frontier, I think, of this discussion, because actually I have these photons which interacts very softly with matter. And then I can create a lot of these entangled states, but actually inside a biological system with everybody bumping with one another, you should have much stronger effects than what I studied. So it should be much more interesting as well. So with that, I would like to call attention to the many people that worked in the experiments in Recife. In blue is just the team at 2022. And thanks for your attention.